In this video, we're going to look at how to graph polar equations with the TI-84. Let's jump right into it. So if you watch the lecture on polar equations and polar graphs, you saw that we had r equals 3, r equals 3 cosine theta, r equals 3 sine of theta, all created circles. If I want to graph those with my TI-84, all I have to do is turn on the calculator and then make sure that my TI-84 is in the correct mode. So I hit mode, and down here we have the option for function. That's like the XY notation. Parametric, that's with x equals a function of t, y is equal to a function of t. And then polar mode is this third one. So go into polar mode and then hit my y equals. When I hit my y equals, the screen should look like this. So R1 is equal to 3, and then I'll graph. Now, obviously, usually I'll zoom square or zoom standard. If I zoom standard, that's number 6 there. Then it might not look perfectly circular because my screen is each unit in the X direction is a little bit wider than each unit in the Y direction. So because of that, this doesn't maybe look like a perfect circle, but it is. If you notice that we've went up 3 units, down 3 units, right 3 units, left 3 units. If that oblong nature throws you off, you can also just go zoom, and then in the square will make each unit in the X direction be the same as each unit in the Y direction. And so that looks a lot more circular. Okay. So there you go. That's all we have to do. Hit Y equals, and then R is going to be equal to that if we're in polar mode. Now 3 times cosine of theta obviously is a graph. Does not have radius 3, but rather radius of a half and laid out along the x-axis. Okay. Another graph that we saw in that lecture was r equals theta. Oh, I'm just hitting this button to get theta, right? My variable key, my variable in polar is theta. So I'm hitting this variable key. As long as your mode is in polar, every time you hit the variable key, you get a theta. So r equals theta, graph that. Here, I only see one loop of a spiral. That's because when I hit my window, the standard zoom goes from 0 to 2 pi. If I want to go from 0 to, let's say, 8 pi, then I can just type in the theta min, theta max, and then graph. And sure enough, we'll get a couple more spirals if we do that. So again, that's that Archimedean spiral that we graphed. Another type of graph that we looked at was rose curves. And these were the ones where we had like 7 times sine of 3 theta. 7 times sine of 3 theta is a rose curve with 3 petals. If I just type that in, again, theta here is my variable key theta. And then graph it. This one looks pretty nice. I can see all 3 petals of my rose curve, and they look pretty darn smooth. One thing we did in our lecture was find out where and when those rose curves hit the pole or the origin, you can see that if I hit trace and I start with theta equals 0, then the XY values are giving me the origin. As I start hitting the right arrow, it's jumping around, and I get back to that origin or the pole when theta equals about 1.047. Now I have a inclination that that's going to be pi over 3 because that looks like about a third of pi. If I want to confirm that inclination, all I have to do is hit pi over 3 when I'm tracing, hit enter, and sure enough, that gives me my X and Y values. Then start skipping around. That looks like 2 pi over 3. And again, if I want to confirm that inclination, I just type that in and see that we do get back to the origin. So that's one nice thing we can do. Now, if you get too many loops, let's say we do 7 times sine of 7 theta. This 7 on inside the argument will give me 7 loops. And then I graph. Notice how each of the loops is not very smooth. The reason why those loops are not very smooth, why they look choppy, is because your calculator is doing a connect the dots problem similar to the way you would do a connect the dots problem um, if you were in, back in kindergarten, connecting dot 1 to dot 2 or whatever, drawing a picture. If you drew the straight lines, this doesn't look, if you draw these connecting the dots, doesn't look very smooth. If I want it to be a little bit smoother, just change the window. Let's say we want to go from 0 to 2 pi, but that's not going to help with the smoothness. The smoothness is going to be helped by using the theta step. Instead of 0.13, let's go 0.01 and then graph it. All of a sudden, everything looks a lot smoother. All of those, and the only reason that is because we have more dots to connect. Again, if I want to figure out where things hit the origin, I'll just hit trace. Here at theta equals 0, we hit the origin. Go out and back. It looks like it hits the origin at about 0.46 or so, or 0.45, somewhere in there. Somewhere between 0.44 and 0.45, it looks like. And so what you would do is you would say, well, what is that? Is that perhaps pi over 7? Yeah, sure is. It's about pi over 7. So just type in pi over 7 and see if that's the right theta value. That gets you back to the pole or the origin. So we can do that with rose curves. We can do that with anything else that we want as well. So for instance, something like 2 plus 5 times cosine of theta, that's going to give me one of those lemniscon, uh, lemonscons, lemmasons. That's better. Lemmasons. And it's going to give me a lemmason with an inner loop. Got a little tongue-tied there for a second. So I get a lemmason with an inner loop. And if I want to trace out that, Obviously, I can do so. Now, because we're jumping by a value of 0.1, that is going to be tracing really, really slow. Maybe I'll skip ahead a little bit. You can see that it looks like we're getting really, really close to the origin. Somewhere between about 1.98 and, well, 1.98 and 1.99. We hit that origin, and then I trace around that inner loop. If I want to speed it up, I can kind of speed up a little quicker and then go back to the origin. Now, in this case, that spot where we hit the origin is not going to be a nice pi over 3 or a nice pi over 4 or anything like that. Um, so what you would do is you would make your best estimate. All right. And so we could do that, and you can get really accurate by changing up. So I know it's between 0.43 and, excuse me, 4.3 and 4.31. So I know it hits the origin somewhere in between there. And I can get, again, really, really close if I just adjust my window and adjust my step. I'm not going to do that right now, but there you go. In any case, this is how we can graph various polar equations and then use the trace feature to see either where we cross over itself or whether it were at specific points. So angle 0 gets me there. Angle pi over 2 gets me over there, and so on and so forth. Hopefully that all makes sense. So that's how we can graph polar equations and then trace out where we hit the origin with the TI-84.